Hello, everyone. Welcome. My name is Sid, and I'm a principal solutions architect been with AWS 11 years. And as we gather here at Inforce, we are actually embarking upon a new era, a new digital world which is fundamentally shaped by artificial intelligence. And in this era, we no longer just protect network security perimeters. We have to secure the very conduits that connect our applications to these transforming AI technologies. This connection is more vital than ever, and it's of great importance. But before we dive into advanced network defense, let's take a step back and look at the fundamental pillars of network security. Our mission at the core aligns with CIA, and I don't mean international espionage. I mean confidentiality, of integrity and availability. Now, in this session, we will be focusing primarily on confidentiality. But before we dive into that, I want to briefly mention what network integrity and availability means and the best practices there. Network availability. We need to make sure that the network is available when needed. So we need to stop traffic attacks that overwhelm our networks and make it unusable for genuine traffic. We can do that by throttling. Now, throttling as a capability exists in many AWS services like API Gateway by default, or you can use AWS WAF, Web Application Firewall, on your load balancers and CloudFront. We also have DDoS protection through AWS Shield, Distributed Denial Service of Attack. Now, it's also important that we take genuine traffic and optimally distribute it. That's where load balancing kicks in. Now, in-region load balancing, we have application load balancer, network load balancer, gateway load balancer. For global load balancing, we also have AWS Global Accelerator, which can distribute traffic across regions. Now, when we take a step back and go into the network layer, we also have BGP ECMP, which can optimally distribute traffic across site-to-site VPN, AWS Direct Connect. We also have GRE-based tunnels where you can load balance when you're setting up SD-WAN peering. And finally, we also want to make sure that we have network redundancy. So if your network fails, then you have something to fail over to. That's where you want to use multiple AZs, availability zones. And not just that, you want to maintain AZ-level fault isolation so that a failure in one AZ does not impact all the other AZs, well, basically your application. And you can leverage zonal shift on load balancing to shift traffic from one AZ to another AZ within your applications. Now, looking at our next pillar, network integrity, we want to make sure that our network remains accurate, complete, and unaltered. Now, there are two ways to achieve it. First is to ensure network traffic integrity. We do this by encryption in transit. So for client to server to server to server communication, we have TLS. Going one layer down, site-to-site connectivity, we have IPsec, which is IP security protocol for VPN. And then on direct connect, we can leverage MACsec or MAC security, which is even a layer down at layer 2. By default, we encrypt all traffic between supported instances in an AZ. You get that by default as long as you're using the supported instance types. And as traffic leaves AWS secured facilities, we are also encrypting the traffic by default. So you get that out of the box. You can also leverage techniques like checksum, where you're inserting a checksum into your packet header, which then gets verified on the receipt of the packet. An example of that is object integrity in S3. The next is network configuration integrity, making sure that your network configuration is unaltered. That's where access control is really key, making sure that you have the right IAM permissions and restrict who can make changes into your network. You can also do configuration validation. We have AWS config change tracking, network access analyzer, and VPC reachability analyzer, which can help you with that. Just yesterday, we announced AWS Shield Network Security Director, which can look into your network, identify misconfiguration, and give you remediation options as well. Finally, you want to monitor and detect in case any configuration changes happen which you were not expecting. Again, AWS config change tracking is a great way to do that. but you also have CloudTrail logs and guard duty, which also has network findings, which can alert you on that. All right, let's jump into confidentiality. Now, there are two main pieces to confidentiality: authentication and authorization. Now, when we talk about network authentication, we need to focus on identity because you're authenticating an identity. In the network security realm, what's an identity? Well, the answer varies based on where you look on the TCP/IP stack. Typically, when we write firewall rules or we define identity, it's based on IP address. This host, this IP can talk to this IP. The packet is coming from that IP address. So IP, like inherently, is an identity of a network host. But then we also have other identities. MAC address is an identity, which we typically don't use a lot. But then we also have ports, and we have application level identity. Now, how do we prove that identity? Let's focus on IP address and ports. Well, if you look at how networking works, when a host comes online, it sends a broadcast packet to a DHCP server asking, hey, what's my identity? Give me an IP address. Now, what attackers can do is spoof and run a DHCP server, a malicious one, and then give the host a wrong identity. Or there's also ARP, address resolution protocol. When a host wants to send traffic to its next hop, it says, hey, who is this IP? Give me your MAC address. And that can be spoofed as well, not in AWS. So VPC is not a traditional network. It does not support broadcast. So how does it handle DHCP and ARP? Well, there's a mapping service, network mapping service, which basically absorbs all the requests. It's a big database, all verified, and then it sends a response back. So it does not work like a traditional network. So there's no way you can spoof IP addresses or MAC in a VPC, right? So that's how you prove identity. Now, this is a screenshot of a session from 2013 where we talk about this. There have been subsequent sessions at reInvent talking about this, so you can go and have a look. There is a flag, ENI source destination check, where our hypervisor, our backend, is actually checking the source and destination and verifying it with the mapping service and blocking traffic if that happens. You can disable this. We enable this option because if you want to run routers or any networking services, you may want to disable it. So just keep that in mind. And finally, we also have application level authorization at ALB and VPC lattice. Now, application level authorization is not technically a network identity, but then a lot of our networking services like ALB and VPC lattice are understanding application level identities and using that to make authentication decisions. Okay, so now we have authenticated a network, but how do we authorize it? How do we control access? How do we give permissions to our networks to talk to each other based on the identities? Multiple ways to do that. One is by creating network isolation, and second is by traffic filtering using firewalls. Let's dive into these two. And also we have application level authorization where you are using actually policies on an application layer through services like VPC lattice. But we'll focus on network isolation and firewalls today. So let's talk about network isolation. Here, what we are saying is we will restrict access to entities, authenticated entities, within isolated boundaries. And within this isolated boundary, everyone's allowed to talk to each other. How do we do that? We can do it two ways. One is by creating routing boundaries, right? So we create a routing boundary, and all hosts within the routing boundary can route traffic to each other. And the second is by creating private connectivity. So we'll create private connectivity between two hosts, and only those two hosts can talk to each other because they are connected by this private connectivity. How do you implement routing boundaries in AWS? Well, if you look at a VPC, that's inherently the most fundamental routing boundary. Everything in a VPC can talk to each other by default, right? But then in reality, you have multiple VPCs, and you want to, and they're different routing boundaries by default, but you want to connect them together. So you bring in VPC peering, transit gateway, Cloud WAN, single route table, and then you basically are enabling traffic flow from any to any in these VPCs. So you're creating a single routing boundary out of multiple VPCs. So the way to look at this will be you bundle VPCs into isolated routing boundaries or trust boundaries. And then you connect these routing boundaries by isolated routers. Traffic cannot flow across these routing boundaries. Traffic can only flow within the routing boundaries, right? How do you implement that in AWS? With the help of AWS Cloud WAN. Now, AWS Cloud WAN is a service, highly available, globally distributed, which lets you create these segmented global networks. You start by creating a network policy. You define where you want your Cloud WAN infrastructure to be deployed into, which AWS regions. Here we select 3 regions. When you do that, behind the scenes, we create CNEs, or core network edges, which are regionally highly available, highly scalable endpoints. These CNEs are fully meshed with each other and exchange routes using eBGP. Next, we create segmentation, right? These isolated routing boundaries. Again, everything in Cloud WAN happens through policy. So on the right, you can see I'm defining the policy, and then everything on the left is automatically implemented by the Cloud WAN backend. So we create 3 segments, production, development, and hybrid. And we say hybrid only can exist in 2 regions. Now, by default, within these segments, everything can talk to everything, right? These are logically isolated routing boundaries. But you can enable a flag called isolate attachments true. And when you do that, these routing boundaries become completely isolated. So nothing in production can talk to each other, and so for development, and so for hybrid, right? So we are basically deleting the routing boundary and making everything isolated. So the next step here is to attach our networks to Cloud WAN, and that's done through Cloud WAN attachments. So we have VPC for VPC attachments, then we have GRE-based attachments for SD-WAN connectivity, where we also support tunnel-less connect, where you don't really have to create tunnels anymore, so no more GRE tunnels if you want. You can also connect transit gateways to AWS Cloud WAN. You can connect Direct Connect natively now to AWS Cloud WAN as well. We enable support for this at last re:Invent. And also site-to-site IPsec connectivity directly to Cloud WAN. Now, once you have everything attached to the Cloud WAN, you still cannot route between them, and they are not associated with any routing boundaries or segments yet. That's where attachment policy comes in. So I write an attachment policy where I am saying, look at the tags of the attachments, and then use that information to automatically associate them to the right routing segment. So once you do that, tags are looked at, and they're associated to the right segments. You can also add an additional human approval. For example, you can say, for production, I don't want my attachments automatically associating to my production segment. I want to add a human approval in there, and that's how this works. Now, when you do that, dev can talk to dev, prod can talk to prod, but you cannot cross segments because they're isolated. So production cannot talk to development, hybrid cannot talk to production and development. That's where segment sharing comes in, so you can share routes between segments. And when you do that, then you can enable traffic flow between different segments as well. So we saw how you can use AWS Cloud WAN to create these isolated routers and then connect different VPCs, which belong to different trust boundaries or routing boundaries, to isolated segments. Now, coming back to our network isolation story, the next is private connectivity, right? Now, in the real world, in the physical world, you can take 2 hosts, connect them with an Ethernet cable, and that's private connectivity. So what does it look like in AWS? In AWS, it's powered by PrivateLink. Now, PrivateLink enables 3 kinds of connectivity. One is to AWS services. This is where your clients or hosts in your VPCs can access AWS services. And here, the traffic is only enabled to the AWS services for which you create the PrivateLink endpoints and nothing else. So no access to the internet or anything like that. The next is you can enable private connectivity from your clients in one VPC to a service provider VPC in another VPC. This is where you can deploy a network load balancer and have your servers behind it, and the clients only get access to what's behind the network load balancer, and they don't get access to the entire VPC, right? So you still have that isolation there. And finally, we added support for VPC resources. Now, we heard a lot from our customers saying, this is great, but we want to share our database across VPCs and only give access to some hosts to my databases, like Aurora clusters or RDS. You cannot put a network load balancer in front of an Aurora cluster. So for that, we added this resource configurations behind a resource gateway. So now you deploy a resource gateway, and you can enable access to multiple resource configurations behind it. Resource configurations can be through Amazon ARN, Amazon resource name like RDS, or DNS names or IP addresses. On the client side, multiple VPC endpoints are created, one for each resource configuration, right? So on the server side, on the resource owner side, it's just one resource gateway, but on the client side, there are multiple VPC endpoints, one for each resource configuration. All right, so that was private connectivity. Now we are still talking about confidentiality and how we can authorize access. We just saw how you can create access boundaries by network isolation using routing boundaries or private connectivity. Now let's jump into our next section, which is traffic filtering using firewalls. Now the concept is very clear. We want to use identities and write firewall rules saying this identity is allowed to talk to this identity. And this will be mainly through IP addresses, ports, DNS names, etc. Now, how do we approach traffic filtering in this world of isolated networks? Well, within an isolated network, you often want to restrict traffic between a particular server and maybe a database which it needs access to. In that case, you would write traffic filtering rules based on IP and ports. But then when you cross these isolated boundaries, maybe this is crossing production environment into a non-production environment, or between an application A to application B, you want to do deep packet inspection. Right? So this is how you approach traffic filtering. So how you can do that in AWS is through various purpose-built services. So for layer 4, port and protocol-based access control, you can use security groups and network ACLs. We also support DNS filtering for filtering traffic based on DNS rules. And then finally, we have layer 7 deep packet inspection. You can use web application firewall, AWS network firewall, or just bring your own firewall using third-party firewalls. We'll talk about all of this in greater detail. Let's start by security groups and network ACLs. Now, network ACLs, I'm pretty sure you all know what that is, but it's something which is deployed on a subnet level. It's stateless, and you define rules on what's allowed into your subnet and what's allowed out from your subnets. Versus security groups is something which you deploy on a host or an ENI. And in this example, we are writing outbound rules on the load balancer saying it's only allowed to send traffic to the web server. And the web server is only allowed to receive traffic from the firewall. And you can see here we are using security group referencing to do that as we write the rules. Now, security groups obviously are stateful firewalls, and you can associate a security group with multiple VPCs in the same account and in the same AWS region. Now, jumping into DNS firewall. Now, DNS firewall is for blocking DNS queries to malicious domains. You can write deny lists or allow lists. We provide out-of-the-box managed rules, which you can get started with. Now, DNS firewall is enabled on or a per VPC basis, so you enable DNS firewall on a VPC, but then you get centralized management through AWS Firewall Manager. And finally, we also have an additional tier called DNS Firewall Advanced, which lets you enable query blocking for advanced DNS threats like DNS tunneling. All right, so let's jump into the next category, which is deep packet inspection. And we have 3 options here. First is web application firewall. Now, web application firewall, as the name suggests, is for protecting your web applications. It's a fully managed service, and it's deployed where your application sits. So if you're using a load balancer like ALB, you can enable WAF on that. If you're using API Gateway, AppSync, Cognito, Verified Access, CloudFront, you just enable WAF and deploy the web application firewall as part of those managed services. Now let's talk about AWS Network Firewall and third-party appliances. Now both of these can be used in a similar manner for deep packet inspection, and we'll talk about how all of these fit in a network from a network flow standpoint. But how do you make a decision on which one to use, especially if you're getting started? Now AWS Network Firewall is a fully managed deep inspection firewall, provides you with IPS web filtering, and it can also inspect encrypted traffic. Now it's a managed service, right? So you don't have to worry about managing it, patching it, even scaling it, or have the high availability of it. Everything's managed by AWS. We also give you centralized management and visibility through AWS Firewall Manager. And we also have a bunch of partner integration, which I'll talk about in a bit. Now, Gate Load Balancer allows you to bring your own firewall appliances and connect them in a highly available and redundant manner. Now, this is great where if you're already using something on-prem or somewhere else, you can use the same technology in AWS. Of course, this will be self-managed, so you will have to manage those firewalls, the licensing associated with it, the patching, etc. Now, when we talk about partner support, AWS Network Firewall has multiple integrations. For example, you can use CloudStrike for your host protection. It can detect domain-based indicators of compromise, let that relay that information to Network Firewall, which can then start blocking it centrally. Or you can have Checkpoint centrally audit and manage your firewall rules in Network Firewall. And on the right, when you're looking at Gate Load Balancer, these are the different vendors or partners, who can integrate directly with Gate Load Balancer and support it out of the box. All right, now we have looked at all the different options which we have for traffic filtering. But you might be thinking, I'm deploying security groups in one VPC, I have a VPC firewall somewhere else, I have DNS firewalls, I have like so many firewall products. How do I manage them? Well, AWS Firewall Manager is the answer, which can help you centrally configure and manage firewall policies. It can help you deploy your firewall rules across multiple AWS accounts. A common strategy which I see is with web application firewall, where a lot of our customers have centralized security teams which mandate a certain set of firewall rules, and those can be deployed across the organization. And in addition to that, individual application owners can deploy their own firewall rules. So it's like a distributed plus a centralized approach. All right, so now we have seen the different options you have, but how do they fit from a network inspection flow standpoint? So let's talk about different traffic flows. Let's start by internet egress. Internet egress is where you have hosts in your VPC which needs access to something sitting on the internet. An example would be, let's say you have a EC2 instance and it wants to update its Python package, or it wants to download some patches. It'll do it through a NAT gateway because you don't want to expose your EC2 instance directly to the internet, so it sits behind the NAT gateway, and you would deploy a AWS Network Firewall in the data path. So the traffic hits AWS Network Firewall, gets inspected, gets sent to NAT gateway, and then out through internet gateway. And the return traffic flows the exact same path back. Now it's decentralized, which means for every VPC, you need to repeat the same architecture. So every VPC has a NAT gateway, every VPC has a network firewall. Right, so you're deploying a network firewall in each and every VPC. Now, the good news is we do NAT gateway offset. So if you have a NAT gateway sitting next to a network firewall in a traffic path, we will not charge you for the NAT gateway hourly cost or the data processing cost, right? So that you get that free. And even though you might have hundreds of VPCs and you deploy hundreds of firewalls, as I just mentioned, AWS Firewall Manager can help you with that centralized policy management. Now, if you were to use Gate Load Balancer with your own third-party firewalls, the network design looks very similar. The only difference is that you will still deploy your firewall appliances centrally in an inspection VPC behind a Gate Load Balancer, and then you will deploy Gate Load Balancer endpoints in each and every VPC, right? So lower cost because you're not deploying your firewall appliances in each and every VPC, so you don't have to wait for hundreds of licenses for hundreds of VPCs. But there is no NAT gateway offset, so you just need to keep that in mind. But you still get centralized policy management because your firewall appliances are sitting in a central location. Okay, so the next is how do we convert that decentralized internet egress to centralized internet egress? Well, you can do that by bringing in AWS Cloud WAN. So the idea here is that your application VPCs can send traffic to AWS Cloud WAN, which gets routed via the centralized inspection VPC out to the internet. This is great. The only thing is you are introducing AWS Cloud WAN, which has its own data processing charge. So you need to keep that in mind. But you get reduced ANF hourly cost. So if you have hundreds of VPCs, you don't have to deploy hundreds of AWS Network Firewall. You're just deploying it once in a centralized inspection VPC. So you're paying only for a single instance of AWS Network Firewall. So you save cost there. The next traffic inspection flow is east-west VPC to VPC inspection. So here the traffic is not destined to the internet, but rather to another VPC. So your source is VPC and your destination is VPC. And the traffic follows a very similar path where it is centrally routed to a network firewall endpoint, which inspects traffic and sends it to the destination VPC. Now, in this scenario, there's an important thing to keep in mind. What happens when there's cross-AZ traffic flow? So the scenario here is that traffic originates in AZ1, and it's destined to an EC2 instance in AZ4. Right, so request is from EC21 to EC24. Now, Cloud WAN by default tries to keep traffic local to an AZ. So if Cloud WAN gets traffic from AZ1, it's going to take it and it's going to send it to its ENI, to its endpoint in AZ1. That's exactly what it does. Now, when the return traffic comes, let's see what happens. Now, the return traffic comes from AZ4. Cloud WAN applies the same logic. I want to keep the traffic local to an AZ. I want to save cost, better latency. But so it sends the return traffic to AZ2. Right? So it goes to a different firewall endpoint. Now, for stateful firewalls, they are going to drop this traffic, right? Because the REST request came to one endpoint, the response to another endpoint. And as long as those endpoints are not sharing state, which they don't, this is going to get dropped. So what you can do is you can enable appliance mode, which maintains this AZ symmetry. So you enable that on this attachment. And then when the response traffic comes back, Cloud WAN is going to store state, a flow hash, and it knows that the request for this traffic was sent to AZ1, so it will send the traffic to the same AZ. Right? So this is really important as you're doing VPC inspection and you want to enable appliance mode. All right, so the next traffic flow is north-south hybrid. So no longer from a VPC to a VPC, now it's from VPC to on-prem or on-prem to VPC. Again, the overall flow is similar. It gets routed via the centralized inspection VPC where you have the firewall endpoint to inspect it. All right, our final traffic flow here is internet ingress. And let's talk about the decentralized mode. Now, this is where you have web-facing applications where hosts or like clients on the internet needs to access them. In the decentralized model, you will deploy your application in different VPCs, and then you will just enable protection on the resources like WAF gets enabled on your application load balancers. And if you have non-HTTP traffic, then you would deploy a network firewall in your VPC. And now every VPC which has this requirement, there will be a network firewall in there. Also, if you're using Amazon CloudFront, we added support for private VPC origins, which means you can keep your VPCs completely private and expose them via Amazon CloudFront. Right? So this is really cool because prior to that, you had to have your ALBs or NLBs or whatever public for it to be added as an origin for CloudFront. And of course, you get centralized policy management using network firewall. I keep reiterating this because a lot of times customers are like, hey, this is all decentralized. I have like 100 VPCs. I cannot manage it. You can manage it using network firewall pretty easily. But there's another model, which is a centralized internet egress, where I've seen customers trying to centralize their ingress traffic as well. So one instance of network firewall, one instance of WAF, and then route traffic to the application VPCs. Well, this doesn't really work very well because in order to do this, you have to put a proxy layer which has to intercept all the traffic, ingress traffic, and then route it back to your application hosts, to your applications. Now you can do this by putting a load balancer in a proxy layer and then adding another load balancer as a target, and there are multiple ways of doing it. But I don't recommend it, because if you have like multiple applications, one proxy layer for all the applications is just a mess. This is not easy. So I generally don't recommend this for most use cases. All right, so let's combine all the flows. Right? So you have distributed internet ingress, traffic coming from the internet. You have north-south hybrid, where traffic is from a VPC to on-prem, on-prem to VPC. We have east-west VPC to VPC inspection, where, remember I mentioned you need to enable appliance mode. And then we have the internet egress, where the traffic originates within your VPC is destined for a destination in the internet. Right? And you can see how you can have a centralized inspection VPC, which can cater for all the flows. So you don't really need to create multiple firewalls, multiple VPCs, etc. Of course, except the distributed internet ingress, which I still recommend it to be distributed, and use web application firewall where you can. Let's talk about bandwidth, because when we are combining all the flows, and I'm saying, hey, just use one firewall endpoint, you must be thinking, but is it highly available? What happens? Is it a single point of failure? Is it a single choke point? Very valid concerns. So when you connect Cloud WAN to a centralized inspection VPC and you deploy firewall endpoints in there, Cloud WAN to VPC attachment gives you 100 gigabits per second per VPC attachment per availability zone. So here we have Cloud WAN ENI in 2 AZs, so you get 200 gigabits for this attachment. And on the firewall side, you get up to 100 gigabits per second per AWS network firewall endpoint or gateway load balancer endpoint. Here we have 2 firewall endpoints, so you get 200 gigabits per second. All right, so how do we scale this? We're like 200 gigabits, not enough. Well, you can add another AZ and another firewall endpoint. So now you have 3 AZs, 300 gigabits for the Cloud WAN to VPC attachment. And then you get 3 firewall endpoints, so you get up to 300 gigabits per second. Right? So you can see how this scales. It's pretty redundant, pretty highly available, and pretty scalable. Obviously, as you're adding additional attachments, additional firewall endpoints, especially if you have your own gateway load balancer with third-party firewalls, keep the cost and licenses in mind. All right, so we saw the different traffic inspection flows and how you can use that with a centralized inspection VPC. I want to talk about how you implement this with AWS Cloud WAN. Now, AWS Cloud WAN makes this really simple through a feature called service insertion. You can single-click insert AWS network firewall or third-party services using just network policies. When we were talking about Cloud WAN previously, I showed you how you write network policies and that automatically configures your global network. It's the same thing. To do this, we create a network function group. Now, a network function group is very similar to a segment, which we saw previously, like a production segment, non-production segment. But network function group is a segment which is dedicated for hosting your inspection VPCs and firewall appliances. This is fully managed, but you still get full visibility into the routing behind it. And I'm going to show you exactly how you configure the policies and what kind of routing happens behind the scenes. So here is our sample setup, which has 2 segments, production and development. I have 2 VPCs in each region. One is prod, one is dev. And I'm showing you the route table of CNE1. Right? That's the regional route table in region 1. It says VPC, dev VPC1, and this is the dev route table. So each CNE will have its dev route table and a prod route table for each segment. Every segment has its own route table, and every CNE has its own localized version of that route table. So CNE1 regional dev route table says dev VPC1 is directly attached, while dev VPC2 is 1 hop away via CNE2. Right? Pretty straightforward. And then CNE2 has a similar route table saying dev VPC2 is directly attached, but dev VPC1 is one hop away via CNE1 because it's cross-region. Awesome. Now my goal here is to inspect traffic between production and development, right? As I said, if you're crossing trust boundaries, then you want to do deep packet inspection. And that's the logic I'm applying here. So I'm routing traffic between production and development, and I want to inspect it. So I create a network function group, and I attach my inspection VPCs to Cloud WAN and associate it with the network function group. Next, I need to write a policy which tells Cloud WAN inspect traffic between prod and dev. So this is how the policy goes. Any traffic exiting segment development send to network function group 1. Now just a correction, in this I'm actually writing a policy to inspect internet egress traffic, not the VPC to VPC inspection, not cross-segment inspection. This is more for the internet egress traffic flow, which I talked about. So traffic originating inside your VPC, and it wants to download some Python packages or some patches, etc., from some host on the internet. So here I'm writing a policy saying any traffic exiting segment development send to network function group 1. And this is how my policy looks. Segment development send to via network function groups, network function group 1. I think it's very intuitive, very straightforward. So when I do that, what Cloud WAN does behind the scenes is it inserts a default route saying 0000 next hop inspection VPC. And it populates network function group with all the dev VPC routes. So let's see an example. So the traffic originates in a dev VPC and is destined to the web. It goes to the development segment. The development segment route table says, OK, this is to the web, so it hits the default route, and it's sent to VPC inspection 1. The return traffic comes back. Oh, the traffic goes to the internet. The return traffic comes back to the network function group. Network function group is populated with all the dev VPC routes, so it knows how to route the traffic back, and the traffic goes back. Right? So everything works great. Now, you must be thinking, I write all of these policies and all of that just for a default route to be added. I mean, I can just go and add a default route myself, which is fair. So let's talk about another scenario where you'll see this really is how powerful this policy writing can be. So I bring in a new region, which is very common. Right? Customers like yourselves are expanding and launching new regions. But as you do that, you don't want to replicate your firewall infrastructure in this new region just yet, because you just have very limited infrastructure in there, and you don't want to bear the cost of additional licenses or whatever it might be. But you still want to inspect traffic. So now the dev route table in region 2 says dev VPC2 directly attached, but to reach the other 2 VPCs, I need to go via CNE1. Great. Now I write the same policy. I say any traffic exiting development send to network function group. And the same automation applies, but now this region has 2 options, the dev route table. It can either send traffic via region 1, US East 1, or it can send traffic via region 3, which is US West 2. Right? So which region do you think it will send? It's sending traffic from US West 1. It makes sense that it should send traffic to US West 2. That's the nearest region, lower latency. But that's not always the case. Right? It can actually choose US East 1 to send the traffic as well, because the traffic selection is based on a predetermined algorithm, and you need to verify and make sure that it meets your requirements. Now, if you don't want that, you can actually add an edge overrides rule, where you can say for US West 1, always use edge location US West 2. Right? So you're deterministically adding in the policy how you want the traffic to be routed. And this is like really powerful, because if you were to implement this yourself using some static routes, it's very difficult. So here we're writing a policy saying for development egress traffic in US West 1, always use US West 2 inspection VPC. All right, so you can see something happens there. I have some of the regions misspelled in the slide, but you get the point. Let's talk about another scenario. Here we write a policy, same policy, but for the production segment. But instead of the traffic being sent to the web, what if I send the traffic to my development segment? Let's see what happens. So I send the traffic to my production segment. The production segment has a default route which gets matched, and the traffic is sent to the inspection VPC. The inspection VPC routes the traffic back to the network function group, and the network function group basically drops the traffic. Why? Because the network function group does not have any of the dev routes. It only has prod routes, as per our Cloud WAN automation in the slide. But what if I add another policy for the development, and now the network function group has the dev routes as well? So if I have the same packet, now it gets routed back to network function group, and then now the network function group has the dev as well as the prod routes, so it sends the traffic back, right? So the summary here is, if you write the send to policy for two segments, you can enable traffic flow between them. Now, if you're trying to do that across regions, there can be a problem. Let's look at that example. Let's finish this traffic flow, so the return traffic also flows back. Right? And then now you have the production and development talking to each other. So if you look at the same scenario, but across region routing, the traffic originates from prod. It's destined to the dev segment. Default route matches. It sends to the inspection VPC, comes back, and it sends to the development segment. Now the return traffic comes back to development segment, matches the default route, it's sent to its inspection VPC, and then the return traffic gets sent back. Now you saw what happened. The request went to one inspection VPC, and the response went to a different inspection VPC. Now any stateful firewall is going to block that. Now if that's what you wanted, great. But if you really wanted to inspect traffic between dev and prod, and you wanted to do it with symmetry so that stateful firewalls don't block the traffic, then you can set up a different kind of a policy where you can say, prod segment, when sent to development, send via network function group. That's it. That's that simple. So the previous one was sent to, and this is send via, right? So that's sort of the main difference there. And obviously in here, you're specifying the two segments between which you want the inspection to happen. For cross-region symmetry, we have two options: single hop and dual hop. Single hop is default, where traffic will be inspected by one inspection VPC, both the response and request. And in dual hop, the request and response will be inspected by both the inspection VPCs. So this is how the policy looks. Here I'm looking at the example of dual hop. So you can see I'm writing the policy saying, production when sent to development, send via network function group with the mode dual hop. Again, quite straightforward, quite simple. Let's look at our prod route table in region 1 and dev route table in region 2, because I'm doing prod to dev routing, so I want to show you exactly how these routes are populated. So when I write this policy, Cloud WAN automation kicks in. And what it does is, for development and prod route tables, it says cross-segment routes. Next hop is in-region inspection VPC, right? So you can see the routes are getting populated in the production route table. For my dev VPCs, next hop is VPC inspection 1 in the same region. And then you can see in CNE2, dev route table, the same thing. For my production VPCs, next hop is VPC inspect 1, which is the inspection VPC in the same region. But the network function group says cross-region routes, next hop is cross-region inspection VPC. So let's see why this makes sense. So traffic originates in the production VPC. The destination is a dev VPC in a different region. Traffic comes to production. It says, OK, this is dev, so send it to in-region inspection VPC. The traffic comes to network function group. It says, oh, it's a cross-region route, so the next hop is a cross-region inspection VPC. Right? So this is how the traffic gets sent to the inspection VPC in a different region. And then the return traffic comes in. It gets sent. It gets sent to development, to the inspection VPC, to the network function group, which says, OK, it's a cross-region route, so it goes to cross-region inspection VPC. So now this is how the traffic gets inspected in both the regions by both the inspection VPCs, both the request and response. Now, all of these routes is automatically populated by Cloud WAN. You don't have to write any routes. You just have to write this policy, right? So that's really powerful. So the next is the single hop. Now, when you change the mode from dual hop to single hop, the automation behind the scenes changes. So now the automation says, in the prod and dev segment, local region, cross-segment route, send it to local inspection VPC, right? So that gets populated in both the routes. But cross-region, cross-segment routes, send it to a chosen inspection VPC. So what Cloud WAN does is, for symmetry, it chooses one inspection VPC and says, okay, this is going to be the single hop inspection VPC, right? Now, again, it makes that decision based on a predetermined rule. It's well documented in our documentation. I'm not going to go into those details today. But there's one inspection VPC which gets chosen. And you can see I have chosen my inspection VPC here. And those route gets populated as well. And NFG basically learns all the dev and VPC routes, dev and production VPC routes, nothing special there. So let's see how the traffic flow happens. Now, traffic originates in dev VPC, distant to prod in a remote region. It comes to development. It says, okay, this is a cross-region, cross-segment route, so route it to the chosen inspection VPC. So instead of sending traffic to the in-region inspection VPC, it sends it to the chosen inspection VPC in a different region. Now, the return traffic comes to production, right? That again gets sent to the chosen inspection VPC, and that gets routed back. So this is how single hop cross-region symmetry is done. Now, if you don't like what Cloud WAN chooses as the chosen inspection VPC, you can override that. So if we have an edge overrides feature, we can say between two regions, here it's called edge sets, US East 1 and US West 2, use edge location US West 2. So I'm forcing Cloud WAN to choose US West 2 as my inspection VPC destination when routing between these two regions. By default, Cloud WAN actually chooses US East 1 because that's the highest priority. So here you can force it to choose US West 2. So you have a lot of control, right? So again, as I mentioned, the policy is the only thing which you write. Everything else, all the automation which I'm talking about, all the routing I'm talking about is just for your visibility into what's going on behind the scenes. But you don't have to care about that. You just have to write these policies, right? So really powerful way of configuring your global service insertion architectures. And then as you can see with this edge overrides, now US West 2 becomes the chosen inspection VPC. And the routes changes, and then that's reflected in the traffic flow here, where you can see now the traffic starts routing via this inspection VPC for both request and response. And then you can see the region in one inspection VPC is all sad, has nothing to do. Okay. Now, many of you might be, that's great, but I'm still like finding these policies a bit difficult to write and like send to, send via, whatnot. Well, the good news is we are in the world of agentic AI. So I'm going to show, I have a demo here on how you can use Amazon Q Developer to actually configure your Cloud WAN's policy creation and service insertion. How many of you have heard the word vibe coding? Show of hands. Yeah, a lot of you, right? So what I did here was I'm vibe coding and creating Cloud WAN configuration on the fly. Again, what I'm going to show you here, I recommend for your development and sandbox accounts just to get started and configure Cloud WAN. But as you're doing it in production environments, don't vibe code. Maybe just use CloudFormation templates which you generate out of this vibe coding. So let's look at this. So I open my command line and I go type qchat. This brings up my QDeveloper CLI. I use /model to change my model to Claude 4 Sonnet. And I put a prompt saying, using state networking profile, analyze my account and provide me a comprehensive overview of my Cloud WAN configuration. What QDeveloper does, it starts making a bunch of CLI calls. Describe global networks, list core networks. As you can see, I'm going to speed this up, get core network policy, list attachments, a bunch of, like, it implemented like almost 10 CLI commands, and it generated all the information, and you can see it gives me a summary. I have two segments, production, dev. I have attachment policy configuration using tags. I have 15 attachments. You can see I have 9 VPC attachments for production development. I have inspection VPCs where I attached but not associated yet. I also have a bunch of transit gateway attachments. It also gives me strengths and observations, and also give me a summary. So my next prompt here, implement service insertion for traffic inspection. 1, research AWS documentation. 2, summarize the key concepts and give me a plan. And 3, provide a step-by-step implementation plan. Include any necessary CloudFormation templates. So what it does is it first goes and reads the AWS documentation. You can see it requests permission here. I give it yes, and you can see it's going and extracting a bunch of AWS documentation. From there, it tells me, okay, now I've understood the key concepts of service insertion. I've done the current environment analysis. Number 3, I am going to look at the implementation requirements. And number 4, it's building a step-by-step implementation plan. So you can see step 4B is tag VPC attachment. So it's tagging, going into my account and tagging the VPC attachment so that it can automatically associate them with the network function group. Step 4C, it's creating a new network policy. So you can see a network policy has been created, and it's writing it to my local disk. And then step 4D is it's going to create and deploy the new policy version. Well, you can see it makes an error. It goes and creates a command, says create core network policy version. It reads the error. It says, oh, I need to fix this. I'm using an incorrect command. And then it executes it's a correct command where now it's putting a core network policy. So it's really nice where it makes mistakes and then corrects itself. It's really cool to see. And now it's executing the core network chain set where it's executing the policy. So it says the policy is executing. Let me check. So it can. So it's now doing some verifications. The policy is live. So you can see here the policy is still executing. This is normal. It takes a couple of minutes. Let me create a CloudFormation template for future deployments and provide an implementation summary. Right. So now it's going to go ahead and take all of that and build a CloudFormation template for me so that I can use it for actual production deployments. It's also creating a test and validation script here, so I can validate that everything is working. So you can see the validation script has been created. It's making the validation script executable. So now it has it has completed the entire process. It's giving me a summary. It's giving me what the key concept summary are, the configuration changes it made. It added tags to 3 inspection attachments. It updated the core network policy. This is the policy. You can see it added send via clauses for production to development, single hop traffic inspection. I didn't ask it to do single hop. That's what it chose. Then it created a CloudFormation template, validation templates. It's also giving me testing and validation strategies with different phases. Connectivity testing, traffic analysis, best practices implementation. It's giving me next steps, and then it finally gives me implementation status complete. Obviously, I sped this up because I wanted to, not have you wait and see each and everything it's doing. So it was really fast. The demo was around 4 minutes or so. The actual implementation took me around 11 to 12 minutes. So in 11 to 12 minutes. It basically looked into my AWS account, identified my Cloud WAN configuration, what attachments I had, my policy, my segments, and then it created a plan to implement service insertion, attached the VPCs, did everything, followed the best practices, gave me a validation script, CloudFormation script, and I did validate a lot of this, and it was all correct. Right? The only thing I'll tell you is, as you start doing this, it was a very important thing where I asked it to read the AWS documentation. So I was actually using an MCP server, AWS Labs documentation MCP server, which lets a Q developer go and read AWS documentation. I didn't want it to rely on its memory. I don't know when it was trained, whether it knows all the latest and greatest. So by reading the AWS documentation in real time, it was getting all the best practices, all the policy examples, etc., and then using it to do a bunch of this. Here, Q developer also has full CLI access into my account, so that's already pre-configured. But once you have some of these tools and these CLI access configured, QDeveloper can really dig into your account and really help you make a lot of this work. So this is the future. So I thought I'll give you an example of how powerful QDeveloper and AI can be helping you configure networks on the fly. All right, so in the grand scheme of things, we were talking about confidentiality, and this sort of wraps up the traffic filtering using firewall section. This brings us to the end of our session. Just to recap, we started talking about the AWS network security pillars, which were mapped to the CIA triad: confidentiality, integrity, availability. This is how you can get a comprehensive picture of network security for your accounts. Obviously, we focused a lot on confidentiality, on how you measure identity and enable authentication and authorization. But as you go back, start digging a little deeper into making sure that you also have integrity and availability figured out well. And that's how you can build a complete defense for your networks end to end. All right, thank you so much. And please fill the session survey. That really helps us enhance our content for next year. Thank you.